Sadhana. Hello. Good afternoon, everyone. I'm audible. Can you hear me?
Yes,
Can
sir.
you? Okay. Thank you. I hope all of are very well. So let me start now. So afternoon sessions, we have two presentations. One is on the hypothesis testing and the p-value and the test of significance. The second session is related to the factor analysis and hands-on exercise in SPSS. Okay, so in this presentations, we are going to see the hypothesis testing and related concepts. Okay, so I think all of you know the data analysis, mostly that at least something. Okay, in general, the data is presented in two different formats. One is descriptive statistics, so another one is inferential statistics. Descriptive statistics is just presenting the data, what it is actually that through graphically or in tabular form or in numerical measures. So in graphical form represents the frequency distributions, relative frequency, cumulative frequency kind of things, bar charts, pie charts. Those things are coming under the graphical representation of the data. So this tabular, then numerical in terms of mean, median, and the measures of dispersions, range, deviations, standard deviations, kind of things will be used to describe the what is the actually the data represents. Usually, it will not say anything about the population parameters, so that it will not represent the characteristics of the populations. Okay, it just show the what is it actually that what data set has, or what the nature of the variables, right? So in inferential statistics, it is not like that. Here usually it is related to the sample and sampling distribution kind of things. Based on the sample statistics, the sample estimators will derive the draw the inferences about the population characteristics. For example, so if you want to, for example, because in general, we are not able to study the each and every objects or subjects are individual in the populations, because the population usually will be larger one. Even it will be lakhs, crores, 10 crores kind of things. So we cannot study each subject in the populations. So in order to even it will also it will be costly and labor requires more labor and time also, that requires more labor and time. Okay, in order to avoid such kind of things, then usually we'll draw samples from the populations, and based on the and estimate the sample characteristics. Then based on the sample characteristics, we will draw inferences about the population, right? So in this case, when but there is a problem in such kind of inferential analysis, because that whenever we draw, whenever we change the sample, then usually the sample to samples, our sample statistics will vary. So we cannot sure that that particular samples will represent the true characteristics of the populations. So in such a case, that we have to ensure that whether the particular our sample is giving the real the true nature of at least approximate the population characteristics. So in order to do check our reliability of the our sample statistics, we are conducting some statistical tests. Those things are coming under this hypothesis testing, confidence interval, and the level of significance. So in this class, we are in this sessions, we are going to see what are all these things. Actually, that just what is the technical things behind this hypothesis testing and the level of significance. Okay. The hypothesis testing, I think many of you know what is hypothesis, and hypothesis testing so partially are something. But in general, hypothesis is just a premises or claim that we want to test actually for example, so there are so many phenomena existing in the society and nature. Scientists may have a different kind of ideas, theories, concepts about those phenomena, but we do not know actually whether these are true, or this theory or concepts are true or not. Okay, so these are all just a statements, but this should be tested so that we can tell that particular theory is um, true or not. Okay, so like that, it is just a claim, and it can also be as just assumptions or some suppositions to be proved or disproved. So what are all the theories we develop, whether it is existing or not, we have to test it and to prove it. Okay. Mm. So and it can also be statement about the particular population or group or societies, whatever. So that in general, the hypothesis is just a statement or assumption or case or claim about the particular phenomenon. Okay, phenomenon in the society as well as in the nature. Okay. So the hypothesis generally have some if any statements said to be a hypothesis, it should satisfy some properties. So that is that any hypothesis should be clear or precise. Hypothesis can be tested through samples. So if any statements which are any statements the statements may be the may represents the fact or myth. Okay, the myth kind of the statements representing the myth cannot be tested, so because usually we do not have samples for the myth kind of things. So when the statement is representing the fact, then we can we can quantify those the characteristics and can do the test. Okay, and it should be the any hypothesis should be stated in simple terms. It should not be any complicated kind of things, right? Then it should consist with most of the known facts, and it can be tested with reasonable time and cost. So that I think so many of the theories are still existing as a theory because of the lack of data to prove those things, right? So that whatever the theory or statements stated as a hypothesis, it should be reasonably tested in at a time, and it should not take more cost or labor requirements for testing such kind of things. If it is not so, that it will remain as a theory as long as it is proved. Okay. So we have there are two different kinds of hypothesis. So one is a null hypothesis. So another one is a alternative hypothesis. Null hypothesis representing actually the current situations, currently accepted value for a parameter. For example, it is currently accepted or initial claims or nothing. We can say that even nothing, no improvement in the current situations, or that we can say that null hypothesis are no difference between the two things or two claims. Like, so why we call it as a null hypothesis in general? So null hypothesis always states the current situation. So for examples, so if we say that the income of farmers at the current stage, before implementing any interventions, is zeros. If it is if we implement any interventions to increase the farmers' income, then it should either improve or it will remain as it is. So if we say that there is no improvement in the income due to the interventions, then it will be stated as a null hypothesis. Okay. So the null hypothesis is usually the claim the current situations. Usually it is a null. That null means that null itself means that 0. So that there is no improvement, no difference between the existing and the interventions due to the interventions. Usually that null hypothesis we stated H0, H0, and the mu naught is existing, the value of the existing thing, and mu is value of the value of the new interventions. Okay, if we say that there is no difference between the value of the null hypothesis and the existing thing and the new thing, then we can it will be stated in equality terms. Okay, null hypothesis always will be stated in terms of equality conditions, that existing and new one always equal. There is no improvement between the two. Okay, so that while that we have another one set of against the null hypothesis, that is alternative hypothesis. Actually it is a research hypothesis that it is just opposite to the null hypothesis. That is if we say that there is no improvement in the any kind of things, then there the other statements will be the no, it is not like that. We can say that there is a improvement. That statement, if we say such kind of statements, then that is called alternative hypothesis. It's just opposite to the null hypothesis. So alternative hypothesis can be three types. Directly it is if it is not equal to whatever, so but it is not whatever the null hypothesis, but alternative hypothesis is not equal to the value of the null hypothesis. Okay, it may be the either way. It that alternative, the value of the alternative hypothesis may be more than null hypothesis value or less than null hypothesis value, so whatever. Okay, but it is not equal to the the value of the null hypothesis. So that another two types is if we can say that alternative hypothesis is not if null hypothesis we stated the value of the null hypothesis mu naught, then alternative hypothesis is maybe more than the null hypothesis. So then while that we can say like alternative hypothesis may be less than null hypothesis. Okay, so that all these three conditions shows that the alternative hypothesis inequality conditions. So that is anyway that alternative the value of the under alternative hypothesis is not equal to the value of the null hypothesis. Okay.
Hello. Sir,
yeah.
Once again, can you explain with an example? Like it's little confusing.
Yeah. Best wait. I will
Null
come.
hypothesis.
Yeah. Wait. Yeah. So here see. So the let's take the example. Average calorie intake is not higher than the recommended dietary allowance after the interventions. For example, if the government tries to improve the calorie intake of school in a school, and giving the some interventions, giving some any kind of food, that fortified foods or nutritional food through midday meal or breakfast kind of things, whatever. So government is intervening to increase the average calorie intake of the students in a school. But here that null hypothesis says that there is no improvement in the calorie intake due to the interventions. Okay, so just like the then alternative hypothesis automatically become the there is an improvement in the average calorie intake due to the interventions. Okay, so like that we can say that another examples, income has no impact on the expenditure and no impact. You have to note that income for the null hypothesis, income has no impact on the expenditure on the electronic items among the low income people. That is that whenever the income increases, we usually people spend more on the luxurious food, luxurious commodities like electronic items, like maybe mobile, laptop, TV, any kind of washing machine, fridge, any kind of electronic. It's a luxurious things. As income increases, usually the tendency of people will spend the expenditure on the luxurious commodities. So it is a, but here the null hypothesis says that there is no such kind of things. Okay, so alternative hypothesis is it is not like that. Whenever income increases, there will be more expenditure on the electronic items. Okay, so then the another one example is a quantity demand of apple is not influenced by the prices of the other fruits. Okay, it is not like that always, but usually that whenever the quantity consumption of apple is highly influenced by the prices of the other fruits. Whenever that when an apple price is higher in a fruit shop, so usually we will go for the fruit for which there is a less price. Okay, so alternative hypothesis here is influence always the price is always influencing the quantity demand of the fruits. Null hypothesis, it is not, it says it is not like that. Okay, so like that, so hypothesis should have some characteristics. So the hypotheses are statements about the unknown parameters. So here unknown parameters that initially we will not know about the value of the statements. Okay, for example, say average price, average quantity of population or samples, whatever. Initially we will not know about these parameters, the quantity, the value of these parameters. Okay. The hypotheses are chosen before the sample is drawn based on the existing theory. Okay, based on the existing theory. For example, if you try to measure the elasticity of the livestock or milk products, it's a theory that whenever the high value commodities are the price highly influencing the high value commodities, whenever um, the prices are whenever the price increases, the quantity, the high value commodities will also, the demand for the high value commodities will always decrease. So this is a theory. So based on the theory, we usually choose the hypothesis, both null and alternative hypothesis. Okay, so null hypothesis is always stated with the equal sign as previously seen. Alternative hypothesis is stated with the inequality condition always. And also that alternative hypothesis is one which is always we try to prove it. Okay, whenever there is an intervention, whenever there is an introduction in the technology, whenever whatever the things we are doing, we expect some improvement or development due to that activities. Okay, so in such a situations we try to prove the alternative hypothesis and disprove the null hypothesis, because null hypothesis says that there is no improvement. Like, okay, so here the null hypothesis one which we always try to disprove it. For example, so here the same things, the higher income has no impact on the expenditure and the electronic items among the low income people. So based on the theory, as income increases, there should be a higher expenditure on the high value commodities. This is a theory. So based on this theory, we can develop our null hypothesis like here, and alternative hypothesis which shows there is the impact on the high luxurious commodities whenever price increases. Like, okay, so both hypothesis can be indicated like this. The null hypothesis can be indicated has a 0. This is a new one, value of the new one, and this is a existing value. And it is the null alternative hypothesis says it is not always like that. It is always not equal. Either it may be positive or negative. Okay. Some more examples here. A new teaching method is developed that that is believed to be better than the current method. Okay, so null hypothesis here is a new method is no better than the old method. The alternative is that new method is a better. Okay, so another one example is a new Salesforce bonus plan is developed in an attempt to increase sales. So here null hypothesis is the bonus plans does not increase sales. Alternative is bonus plans increases the sales. Okay. So another one example is the new drug is developed with a with the goal of lowering the blood pressures more than an existing drug. Here the null hypothesis is the new drug does not provide lower blood pressures than the existing drug, and the alternative is that a new drug lowers the blood pressure more than the existing drug. Okay. So in each case, the rejection of the null hypothesis provides a statistical support for our research hypothesis. So that's we try to prove that in a research we always try to reject the null hypothesis and accept the alternative hypothesis. Okay. So some more concepts are here that null hypothesis and alternative hypothesis are competing statement about the population. That means that both hypotheses will not happen at a time. So for example, we cannot say null hypothesis is true as well as alternative hypothesis is also true. We cannot say. So both will function in opposite direction only. When null hypothesis are true, then alternative hypothesis must be a false. When alternative hypothesis is true, then null hypothesis must be a false. Okay, so that both will move in either one directions. That is the opposite direction only. Both will not move in the same direction. Okay. Ideally, the hypothesis testing procedure should lead to the acceptance of the null hypothesis when null hypothesis is true, and reject the null hypothesis when null hypothesis when alternative hypothesis true. Okay, so in any research we usually derive the decision regarding the rejection of the null hypothesis or accepting the null hypothesis. We will not say the we will not take decision about the alternative hypothesis. Whatever, wherever, we'll say usually rejecting the null hypothesis or accepting the null hypothesis. Okay. So so unfortunately is that whenever we take a decision in rejecting or accepting the null hypothesis, we may, as a human beings, we may commit the error that we may take a decision wrongly. That, for example, so let's see here, whenever null hypothesis is true, if you accept the null hypothesis, this is a correct decision. But whenever the null hypothesis is true, we may also reject the null hypothesis. Okay, so this is a error. This error is called type 1 error. Like that, whenever the alternative hypothesis is true, we can reject the alternative hypothesis. This kind of error is called type 2 error. Here, that when compared to the type 1 and type 2 error, the type 1 error is more important than the type 2 error, because here that any statements regarding the null hypothesis, just we have the improvement. Okay, we not have the improvement. Suppose null hypothesis is true, there is no improvement due to the some interventions. Okay, it is a true. Suppose we may commit to the rejecting this null hypothesis when it is true, then that means that we are accepting the alternative hypothesis. There is no there is a improvement due to the interventions. If we accept when null hypothesis existing, then that means that due to improvements we will further invest more and more on that to improve the activities, to more invest cost and resources, and make policies regarding the in favor of the alternative hypothesis. But actually there is null hypothesis is true. So in such a case, there is a more cost regarding the type 1 error. when compared to the type 2 error. So when we commit the type 2 error, that means that just we are accepting the alternative hypothesis when it is false. So in such a cases, even if it is a false, then we can improve over in the time period, future periods by drawing the different kind of samples or any kind of. So here there is no cost involved in terms of resources, time, any. So in such a cases, we the type 1 errors will be the will be the more costly. Okay. So how to measure this type 1 error? We can measure this type 1 error in terms of probability. That probability of committing type 1 error is the type 1 error is the probability of rejecting the null hypothesis when it is true. Okay. So actually this type 1 error should be minimized in our research. Okay. So examples for the type 1 error, a study claims that new community intervention program significantly reduces the crime rates. But in reality, the effect is due to the random variation and the programs has no actual impact. So the type 1 error, why this kind of error is happening? So because of the sampling variations. If we draw one sample and estimating sample estimates and drawing the informations about the population parameter, if you draw another one samples, that will give different kind of results. If you draw another one samples and so on, then each samples will give different kind of estimates. So that it is finally we will it is very hard to choose which samples will be the true representation of the population characteristics. So in such a cases, this is called random variation or sampling distribution or probability distribution kind of things. Okay. So because of the sampling distribution or random variations, our null we may commit the type 1 error. Okay. Researchers conclude that increasing the minimum wage leads to the higher employment, but in reality, the observed increases is due to the other type of other kind of factors, and the true effect is neutral or negative. Okay. Then our company believes that a new advertising campaign significantly pushed the sales based on the study, but in reality, this may not be like that. The increase in just is just the random fluctuations like random samplings. Okay. And the campaigns has no real effect. So all these represents the a type 1 error. Okay. So all these are maybe due to the poor quality of data, random chances, and sampling distributions. All these three represents the sampling distribution only. Okay, random chances. So in such a cases, how to control the type 1 error? That process is called the application of hypothesis testing or significant test. So many applications of hypothesis testing are like that only. Most application of hypothesis testing control for the probability of making this type 1 error. Hence, our task is to reject the to accept or reject the null hypothesis, but we cannot determine how confident and we can be with the decisions. It may be the we may have the chances of committing type 1 error, right? So we can so the committing type 1 error is the probability of committing type 1 error is called the level of significance in the statistics. So what is it actually? So the level of significance is the size of the type 1 error measured through the probability rejecting null hypothesis when it is true, and always it is indicated as the alpha and determined in advance and stated as the level of significance of the hypothesis. That means that the level of significance will be stated before the research start. Okay, before the analysis start. That is the in practice, the who is doing the research is responsible for the choosing this level of significance, that amount of error we are committing the type 1 error. Okay. By selecting alpha, researcher can controlling the probability of making a type 1 error. Mostly this probability of committing type 1 error is a 1%, 5%, and 10%. These three probability significance will be is always are always used in the research hypothesis testing. If the type 1 error, so all this means that if the type 1 error is fixed at 5%, that means that we are having the only five chances out of 100 that we reject the null hypothesis when it is true. Okay. So how to measure the level of significance quantitatively in statistics? So before that, we should understand what is the sampling distributions. Here, see one examples I have given here. Suppose we are studying the average income of workers in the country. So the true population mean is 50,000. If you take a sample of 3,000 workers across country and found the estimated value, the X bar, that average of average of sample is 52,500. Can we say this the 50,000 and 52,000 are really different? That means that the sample values and the population values are different. We cannot say surely, because this the excess 2,500 may be due to the random sampling, that sampling fluctuations are the error, the sampling error. If there is no sampling error, maybe this estimated sample value may be equal to the population mean. Okay. So because of this sampling error, we have the difference. Okay. So now our task is to whether it is truly this estimated value is truly different from this one or not. So this is sampling distributions. So for example, let me explain here. So if we take a population, if you take a sample, n number of samples from a population like this, we can estimate different kinds of average for each samples. Okay. So each samples, it is not necessary to have a equal between of the each sample representing the equal to the population parameter mu. Okay. So there will be some sampling distributions. Okay. So these sampling distributions can be the average of all the samples can be plotted in a frequency. If you take a frequency distribution, so we will get graph like this. I think many of you know the bell-shaped curve, the normal distribution. So it shows that the samples are distributed around the mean value. Okay. So if our estimated value is something different from the populations, we can say that there is a difference between the population parameter and the sample statistics. But because of the sampling error, we cannot say truly that. If it is said that if both are different without considering the sampling error, then that means that we are committing the type 1 error. That is we are rejecting the null hypothesis. That means that estimated value and sample values are not equal. Okay. So we are committing the type 1 error like this. So if you plot the sampling, each samples the expected sample means, if we can get normal distribution of this like this, which distribute around the mean values. Okay. So now we can say the how how far away our estimated values from the sample value, and also that we can say if we calculate the standard error, that sampling error, then based on the errors we can also say that at how much the probability of have a confidence level which approximate the population parameters. Okay. So here, if we say that out of 5 chances we have the committing type 1 error out of 100, then 95% is a confidence level. So that means that 95% of the chances may represents the truly the population parameters. Okay, population parameter. So if you so if you okay, see. So if you say this 5% chances of committing type 1 error, then that is a very minimal amount that will be distributed at the end of the distribution curve here. Okay, so now our task is to if it because it is the area under the curve is representing the population probability value, that is equal to 1, the sum of the probability value. If it committing the type 1 error 5%, so here is a 2.5%, here is a 2.5%, so will represent the 5% error. So now our task is to that our the estimated value should not fall in this category. If it is fall in this category, then we are committing the type 1 error. Okay, so this is in unit. This distance is measured in respective unit of the variable. Then we can make it as a standardized value, like using the z test, t test kind of things. So here I have taken a z test. So z is just the value for the difference between the ratio between the difference between the actual and mean value and the standard error, the standard deviation or standard error. Okay, so here is the standard deviations. So we can measure which distance our estimated values from the mean values by adding the standard error like this. Okay, so if our so for example, so if our estimated value and population values are equal, then we will get 0 here. So 0 means that z is equal to 0. So then that our value, the z value will be the 0. So whenever our estimated value and probable population values are equal. Okay, in that is the case, then if the the z value is 1, then it will be here. Z is value is 2, then it will be our x value will be there. Then z is 3, then our x value will be located here. Okay, so this can be told us that one standard deviation, that our x value is deviating from its mean value at one standard deviation is two standard deviation and three standard deviation. One standard deviation covers the almost 68% of the total distribution, and two standard deviation covers the 95% of the distribution, and the three standard deviation covers the 99% of the deviations, right? Like that. So by measuring the z values, we can say that at what how far our estimated value is deviating from its mean value. Okay, so by looking at z values, we can say whether our estimated value is fall in this tail regions. If it is a fall in this tail regions, then we can say that the probability of committing type 1 error is more. Okay, so that is less. Then we can reject the null hypothesis and accept the alternative hypothesis. Okay, let me explain in detail in next. So here we can estimate the probability value for one standard deviation, two standard deviation, three standard deviation, like 68, 95, 99. So if it is for what about the 1.5 standard deviation, 2.5 standard deviation, or 1.9 standard deviations? So these probability values are just calculated and tabulated in as z tables here. By looking at the z values here, the estimated z value and its decimal, we can locate the probability of the falling the location of a particular estimated value. For example, if z value is 1 here, then we can say this 84% of the probability. Like, okay, if it is a two-tailed test, then we should take into consideration of the here. Okay, So like this, if we take a 1.445 value of the z, then 1.4 and this 5 decimal 0.5 will be measured as a probability value of the desired value. Okay, so like that we can locate the probability value of by looking at the z values, we can locate the probability value of the existing the estimated value. Okay, this will be useful in estimating the probability of committing type 1 error. So here, let's see here. So in hypothesis testings, test of significance, the case of Z test. Here, see the decision. In null hypothesis, our decision is actually to accept or reject the null hypothesis. Okay. So here, see our null hypothesis is estimated value is equal to population parameter. So that means that there is no difference between the both values. If we say our alternative null hypothesis say that both are not equal, then we have to whether these are true, whether it's true or not by measuring the z values. If it is null hypothesis is true, then both are equal. Then both are equal means that z value is 0. So here z value is 0. So that means that there is no difference between the true and estimated value and population parameter. So if we say that z values, if something there is a difference, some difference is here, or estimated value is here, we can say this the estimated this z values, that the positive or negative values of other than 0 is showing the evidence against the null hypothesis. In this case, we cannot reject the null hypothesis and accept the alternative hypothesis. But this difference, we cannot sure that this difference is just due to the interventions or whatever, or anything else, example sampling error, or just a chance. So we cannot sure. If it is if there is no sampling error, rejecting the null hypothesis is leads to the false decisions. Okay, here rejecting the, so as z value is departing from the 0 in either sides, shows the higher evidence against the null hypothesis. Okay, so that but we cannot take decision that we cannot reject the null hypothesis because due to the sampling error. Okay, that for the small values of the z values, but if z value is larger one, there is a chance to for the small sampling error. So this, if it is if as previously discussed, if it is considering about the committing the type 1 error, that the level of significance, then as our estimated z value must fall in this category. So that should be more than the probability value of the table value. So this means that if z value is more than that, so the committing type 1 error is less. For example, if you take committing type 1 error is of 5%, this both sides 0.5 0.5 will sum is 5 will make 5%. So if z value is more than this means that committing type 1 error is less than the 5%. So we can reject the null hypothesis and accept the alternative hypothesis. So like that we can take a decision whether the hypothesis should be rejected or not. Okay, so like that the same things, the same concepts is applicable for the z test, but only difference is that the t test, the only here that z test here there is assumption that we know the standard error or standard deviation of the population parameter. But here, since actually in practically we do not know about the population parameter, we usually take the sample standard deviations. In such a cases, whenever the sample is dealing, then in such a case we usually use t test. Okay, So that, but the concept is more or less similar, rejecting or accepting the null hypothesis. Okay. So that so based on the type of the alternative hypothesis, we have the three different kinds of test. So one is a left right test. If the value of the alternative hypothesis is less than the population parameter, if it is more than the population parameter, this is the right tail test. If it is if the inequality is in either way, then that is called two tail test. Okay. So this so far we have seen that what are the probability value of level of significance and different kinds of hypothesis testings, and how to take the decision regarding the rejecting null hypothesis and alternative hypothesis. So these are all the major steps to in testing the significance hypothesis testings. First, we have to formulate the hypothesis. We have to say that which is a null hypothesis and which is an alternative hypothesis. And we have to select the significance level, whether that our decision takes place 5% or 10% or 1% level of significance. We have to say in before the analysis taken, and choose the appropriate test, whether based on the our kind of data, the parameters unknown or known parameters about the population characteristics. We can use the different kinds of test, t test, z test, high square test, f test kind of things. Okay, so we have to choose the appropriate test accordingly we want. Then we have to calculate the test statistics, that is a calculated t value or z value. Then it should be compared with table values. So based on the table values, that our decision calculated value and table value, we can take the decisions. Actually, that calculated value should be more than the table value. Okay. And also we can take decisions based on the committing the probability values. Actually, that the probability will come along with the software analysis. All the software analysis, any kind of regressions or any kind of regressions, we have the probability values. So we need not to check the table values of the respective test statistics. If you look at only the probability value, you can say whether the particular the hypothesis be rejected or not. If in such a case that 1% level, if he stated 1% level of significance, that the probability value should be less than 0.1. If it is a 5% level of significance, it should be less than or equal to 0.05. Then if it is a 10% level of significance, then it should be less than the 0.1. Okay, these are all the decision the scenarios. So if the absolute the test statistics calculated value is more than the table value, then we can reject the null hypothesis and accept the alternative hypothesis. That means that there is some the interventions is true. Okay. So if you fail to reject the null hypothesis, if the test statistics is less than the calculated value. Okay. So here I have given some examples. Here see, so the purpose when we comparing the sample mean with known population standard deviations, typically for large sample size, we can use a one sample test like this. For example, a survey of 50 households shown on average monthly expenditure on food of the 12,000 with a known population standard deviation of 2,500. We test if this is significantly different from the national average 11,500 up to 5% level. So using this Z test statistics, we can get the value like 1.41. So this might be, if you compare this 1.41, this so as my experience, this will be definitely at 5% level. This will be the lesser than the table value. So we can, in this decision, we cannot reject the null hypothesis. We should accept the null hypothesis. Okay. That means that no significant difference between the population and national average and sample. Okay. So like that for t test, the population standard deviation unknown, and the sample size is less than 30. If this sample size, wherever the sample size is less than 30, we can use the t-test instead of z test. So here an example. So in such a case, if we calculate the t-values, we have calculated the t-values at 2.63. As my experience in this, that at 5% level, 2.626 might be more than the table value. So in this case, we can reject the null hypothesis and accept the alternative hypothesis, so that there is a significant difference between the each regions. Like, okay. So the another one test is a major test is a paired t-test. It is a two sample test. Um, um, so here that we measure the two different kinds of category, the value for the two different kinds of category for the same respondents. See here, for example, so if you take a farmer, so estimate the income before and after the implementation of the minimum support price, and take a, so whether these difference are true or not, we can take we have to test the significance of this by using this the same t-test. So here also we can say that we have calculated the 11.8. This, in this case, we can reject the null hypothesis and conclude that there is a significant increase in the farmer's income due to the minimum support price increase. Okay. So like this, we have so many test statistics. So due to the paucity of time, I don't want to go in deep. It's just a orientation. So hereafter, you have to look for the deep analysis and the interpretation kind of things. So I have given some examples for different kinds of test of significance test when the population parameters is known and the sample size is more than 30, and the t-test will be used for even sample size is lesser than 30, and the do not and know the about the sample parameters. Okay, and the paired t-test, ANOVA 2-way, high score test, F-test, linear regressions. So in many kind of analysis, always this test of significance is used. Okay. So I think this hands-off exercise morning, Dr. Felix have done in SPSS. I will show some few things. I think we have only 5 minutes. So let me.
Yes, sir.
Yeah.
Doubts, sir.
Yeah. Just it's we are running out of time. Quickly.
Sir, okay, sir. Sir, where does the value 1.96 comes from, sir?
Which one?
Sir, in that Z value 1.96, what is that value? Sir?
Yeah. That is table value. I have told you that we have to look at the table value and the estimated value. Here we have estimated value. Okay.
Okay,
So
sir.
this is a table value. Okay. If our estimated value is more than the table value, we can reject the null hypothesis. If our estimated value is less than the table value, we cannot reject the null hypothesis and accept the alternate. So yeah, we cannot reject the
Is it is fixed value, sir?
insignificant.
Because in sample size
this is
determination also
only
we
I have
use this value for calculation.
Yeah, this is a table value here. Okay, I have shown you. So you have to look at the Z value. So wherever Z value is 1.4 here. So, and if it is a two-side test, there will be a value. If it is less than that estimated value, then if it we can reject the we cannot reject the null hypothesis. Okay, just why it's just a orientation. So hereafter you have to look at the you have to go in deep. Okay, right? Okay. So let me do some hands-on exercise. Okay, that all of you have. I think you might know. It have.
Sir, excuse me, sir.
Yeah.
Sir, how do we choose the level of significance, like whether
So
it is
that's one slide I saw that it's based on the researcher. It's under the control of the researchers. You can choose 1%, 5%, 10%, any kind of level of significance.
Yeah.
Okay, that's based on your requirements. If you believe you are committing type 1 error is or type 1 error is very less, then you can choose 1% level of significance. Okay.
Okay.
So whatever the level of significance, it's under your researcher hand.
Yeah.
Okay.
Thank you, sir.
Yeah. So I think all of you know the how to operate the test the SPSS. How to import data, do analysis. So let me do this two sample test. So here we have the yeah the value for the profit of different shops in rural and urban regions. If one is called as rural and two is called as urban, then we can whether this profit whether significantly different from the rural and urban regions, we can do by doing the two sample test, like compare the means and independent sample test. So just we have to select that our desired variable that profit, and we have to also select the groups representing the rural and urban. Then yeah, you can set that 1%, 2%, 1% or 5%, 5% or 10%. If we say 1%, then we can give 99, or 10% 90. So by default it will be always the 5% level of significance. Then yeah, define group, then give click here, see. So here I have told you that by looking at the significance, the probability of committing type 1 error, always that wherever you are the result tables gives the probability value, that means that the probability of committing type 1 error. So our level of level of significance is 5%. So this probability of type 1 committing type 1 error should be less than 5%. So here it is less than 5%. Then we can reject the null hypothesis that both are not same. So both are same. Okay. So this means that accepting the null alternative hypothesis that both are different. Okay. The both rural and urban profits for the different shops is a different one. That means that the whoever running a shop in urban may get and rural the profit will be the different. Okay, so like that we have to interpret. I think it's a time running out of time, so there are like that we have to do we can do many kind of test of significance. So that this is the base the hypothesis, this is the base for all kind of hypothesis testing, whatever the okay. Wherever the statistics and research methodologies are applicable, all in all the places, this is the basic for the rejecting null hypothesis and accepting the alternative hypothesis. Thank you. So whatever the doubt, you can leave a message to the organizing committees, so that only the fruitful and effective comments will be definitely answered. Thank you. Thank you for listening so far. We have a 15 minutes break. Then after the break, we'll meet again. Yeah, welcome back to the second session. Are you there? Can you hear me?
Yes, sir.
Yes, sir.
Good.
Yes, sir. Yes. Yes, yes.
Yeah. Shall we go on? Okay, then in these sessions we are going to discuss about the so what is in general what is multivariate analysis, and in particular what is factor analysis. What are the concepts behind the techniques involved in the factor analysis, as well as principal component techniques. Okay. So I think so you know that what is the difference between the univariate techniques and bivariate techniques and multivariate techniques. So univariate techniques is in general it is related to the single variables. So just studying about the characteristics of the single variables, whether it is numerical and non-numerical data. If you study about only the single variables, it is called univariate techniques. For examples, the t-test, z-test, and different kinds of measures of central tendency and variability. All these for a single variables, all these coming under these categories. Okay. Um, so that multivariate is just opposite to the um, uh, univariate analysis. Here that it includes multivariate includes the interrelationship between. Here that usually that it interested in knowing about the what is the relationship interrelationship between the more than two variables. It may be cause and effect, or it may be the degree of association between the two variables. Okay, but it involves the more than one variables. So that variation in the one variables may affect the may be related to the variation in the another variables. Okay. So here that there are so many technically there are so many things under the multivariate analysis. So particularly these dependence and interdependence techniques are major which are related to the factor analysis and the principal component analysis. Okay. So here dependence means that one variable here also that involves more than two variables. Here one variables will be treated as a dependent variable. Other variables will be treated as independent variables. This independent variation in the is independent variables may cause the variation in the at what extent the variation existed in the dependent variables. That is a cause and effects kind of thing. Usually such kind of dependence analysis are related to the regression analysis. Regression just estimate the cause and effect of independent variables and the dependent variables. But interdependence techniques are not like that. Here there is no cause and effect. That means that there is no dependent variables here. All are called independent variables which are just related, so that correlated. Right. So here it is just focusing on the exploring the relationship between the variables without a predefined dependent variables. Okay. Here that mostly that factor analysis and principal component analysis are coming under these categories. Here just the variance and covariance of the different variables are will be taken to develop a new kind of factors or variables which represents the different kinds of trend kind of things. Okay. So under multivariate techniques, we have different kinds of analysis. Like as I told you in the previous slides, that there is a dependent techniques and interdependent techniques. Dependent techniques involves one dependent variable and more than one dependent variables. Like the one dependent variable is regression, multiple regressions, large conjoint, these kind of things. Then so interdependence techniques variable that we discussed earlier, that variable are only interdependent. So there is no cause and effects, which are mostly dealt by the factor analysis, confirmatory factor analysis, cluster analysis, multi-dimensional scaling, like kind of things. Okay. So these are all the major multivariate techniques. Mostly this factor analysis and PCAs will not have any dependent and independent variables. All are treated as same variables. Okay. So here multiple regressions, the dependent variables may be continuous. So type of dependent variables that will differ based on the different contexts. So like, okay, I don't want to go into this table. So let me explain the what are the principal component analysis and factor analysis. So why we need this? So in practically that these are all the methods for identifying the structure within a set of variables in large size that are difficult to interpret. For example, it happens in marketing side of things. So for awareness or preferences of a particular product by the consumers may be affected by the so many factors, even up to it may go 500 variables. So that our marketing agencies cannot analyze all these 500 variables individually, and will not are not able to come to a conclusions. So in such a cases, this they can group the different kind of variables, the similar kind of variables, into different kinds of groups or factors like. So based on these groups, they can take marketing decisions, kind of things. Okay, like that, such kind of situations may exist even agricultural sciences, science backgrounds. Even it is applicable in the genetics field also. So because of that, one factor, the changes in the values of the one factors may be related with many other factors. Okay. So it's just this two analysis are just done by grouping the variables based on the intercorrelations among the variables, and finding a few factors based on the similar variables. So let me explain this with this. So let's consider this vector space. This space is a vector. Here we have plotted, we have factor 1 and factor 2. We just assume, and there are so many variables representing the consumer preferences for food commodities. Maybe it may be the organic food. Okay, there are so many factors. So these some factors, some variables may be related to the, if for example these factors are completely independent. How we can say this? If the factor 1 or factor 2 are at the distance of angle 90 degree, then we can say that these are not related. If the angle is less than 90, then we can say that that factor 1 and factor 2 are somewhat correlated or related. So like that, we can also take different kinds of metrics or statements regarding the organic food commodity. So we can also measure the relationship between the factor 1 and respective variables by looking at the degree of the 90 degree angles. If two variables, if factor 1 and another one variable are perfectly coincide, then we can call it as a perfectly correlated. That is a one. Like if factor 1 and some variables are at the angle of 90 degree, then we can say that these two variables, this variable and these factors are not related. So like this, if in a vector space, the variables or attributes may be related to each other. These related attributes may be associated with one factor. Okay. So like this, in such a situations, we can easily group the factors, the variables into one factor, and the respective to the group to the respective factors, like okay. So actually, what is a factor? So a factor is an underlying or hidden characteristics that explains why different things are related to each other. So this there is a factor. It's a value which explaining the how uh, um, the variance of related different variables, related variables are measured. Okay, that, it's just an index. Okay, it's an abstract form of the variation expressed by the different variables on the one factor. Okay, it's just like a secret ingredients that influences the how multiple variables are connected. Okay, so for example, let's say on examples, if you are studying the people's health, factors might represent things like exercise habits or diet quality that affects the several health related measures like weight, heart rate, and energy levels. So these are all the variables, but these are all unknown factors. Okay, so we have to, whether these are related to these factors, we have to, that our task is to find through the factor analysis or um, principal PCA. Okay, so in both we try to find these hidden factors by looking at these hidden factors by looking at the patterns in the data, grouping similar variables together, and understanding what common things is influencing them. Okay, these factors are not directly observable but are inferred based on the how different variables behave together. Okay, so let's take on another one examples, real-time examples. So a researcher wants to understand the underlying factors influencing the consumer preferences for organic food products. They conduct a survey collecting responses on 10 different statements measuring attitudes, perceptions, and behavior towards organic food. So each are each statements are the just Likert scale, 5-point Likert scale. So see here. So these are all the 10 statements regarding the food commodities. So by buying organic food because it is a healthier, it is because it is environment friendly. Organic food tastes better than the conventional food. Like there are different kinds of 10 different kinds of statements, but initially so we do not know about the interrelationship between these statements. Okay, how these are behaving. Once we done, but we can come to know about the interrelationship between these 10 statements, these 10 attributes, by looking just calculating the factors. Okay, so by if a factor may give a group like all these 10 statements into 3 different kinds of groups, like health and environmental concerns, price sensitivity, accessibility, perceived quality, and brand preferences. Okay, so before so after estimating the factors, we came to know these are all the groups, so the major groups, like okay. So it is likely that these 3 items together measures the satisfaction with the products. Through the application of PCA and factor analysis, we can determine whether a single factor represents the 3 satisfaction items well. Okay. So now look at there is even PCA and the FA are seems same. Then there will be some key differences between the PCA and the FA. So while PCA and FA are very similar in the way they are arrive at solutions, they differ fundamentally in the assumption of the variable's nature and the treatment in the analysis. That is the first one, that PCA tries to group the variables, and the factor analysis tries to identify the latent variables. So here PCA just it will not show any kind of pattern or just to group the variable PCA, but factor analysis identify the kind of groups. These each one are called latent variables. before analysis, I think we will not know about this variables. After factoring, grouping the factors, there is a chance to come to know about the new variables. This may be called as new variables, that is latent variables. These things are dealt in the factor analysis. Okay. So technically, there is a difference in the procedure of extracting factors between PCA and FEA. The first, the PCA will take all the common variants, so that expressed by all the variables, while the second one leaves the unique variants expressed by the variable itself and take only common variances. Let's see this, what are the common variances and unique variances in later slides. Okay. To do these differences, the methods follow different research objectives, which dictates their areas of applications. So there are also some key differences between the PCA and factor analysis. PCA, for our previous examples, the 10 statements regarding the organic food, here the PCA reduces the fewer principal components, explaining the maximum variance. It can be used as an index, and name it as an organic product awareness score, like. Okay. But see, there are EFA and CFAs. This means that exploratory factor analysis and confirmatory factor analysis. So there is two different kinds of factor analysis. So exploratory factor analysis means that we have to explore the under this that usually we explore the latent variables, what are possessed in the among the different kinds of variables. Okay, for our previous examples, we can identify the factor related to the health, price, and trust. Actually, this before the analysis, we will not know about this. After extracting the factor only, we will know about these factors. These are the latent variables. So this, just understanding the underlying dimensions. Okay, but confirmatory analysis is not like that. Before the analysis itself, we know about the categories of the statements. Okay, so we do confirmatory analysis just for whether they are the same or not. Okay, by just doing the confirmation, we can check. So for example, if you know the state different statements or different attributes related to the health, price, and trust before the analysis itself, so in the under the confirmation analysis, we can confirm by looking at the variance and covariance of the different variables, the attributes. Okay, so these are all the major difference between the two factor analysis. So far we have seen that what is a factor analysis and PCA. So how to extract this factor? So what are the things to be considered? These are all the steps. So first we have to check the requirements and conduct preliminary analysis, whether related to the data or variables, and extract the factors, and consequently determine the number of factors, interpret the factor solution, and evaluate whether the extracted factor is fit or not, then compute the factor scores finally. Okay, so let's see one by one all these steps. So first step is check the requirements and conduct the preliminary analysis. So under this stage, there are different criteria. Before so first is are the measurement scales are appropriate, that our variables. I think in morning sessions, Dr. Felix might have introduced about the different scales of the variables and the data. So for example, nominal, order, interval, and ratio scales. So we have to choose the appropriate scales of the variables. Then we have to consider is the sample size are sufficiently large or not. Then are these observations independent? The observation means that the respondents, each respondent are different subjects are not interrelated. like that. And are the variables are sufficiently correlated, because this is both analysis are completely related based on the variance and covariance and correlation between the different kinds of variables. The correlation must be checked for the further proceed of the analysis. Okay, so first we will check among these four, that first we will check the are the measurement scales are appropriate. So we have the nominal, ordinal, and interval ratio scales. So the nominal scales are not at all applicable for the factor analysis kind of things, because for the nominal, I think you might know the meaning of the nominal variables. Where for the nominal variables we cannot do any kind of numeric analysis. Even we cannot take averages. We cannot estimate the average values. Because of this, we cannot use a nominal data like gender, religions, brand, regions, rural and urban kind of things. Okay, so ordinal data can be used at certain context. That is that ordinal data, it's just the values are order, but the interval may be different between the two values. But in case of if this the interval is between the two values are equal, then we can use this ordinal variable for the analysis. Like for example, Likert scales. So Likert scales, 5-point Likert scales means that 0, 1, 2, and -1, -2. So each values have the equal interval between the two values. Okay. So in both interval and ratio scales can be used highly for the factor analysis, because we can do all kind of measurements for this interval and ratio scales. Okay, so we can do PCA and factor analysis for these two kind of variables. Okay, then we have to check is the sample size sufficiently large. So here we have some thumb rule. The number of observations should be at least 10 times the number of items used for analysis. Okay, if we have 10 statements or 10 variables, then our sample size should be at least 100. If we have 50 statements or 50 variables, then our sample size at least should be 500. So like that, 10 times the sample size should be 10 times of the variable we are going to use in the factor analysis. Okay. So other techniques are there. By comparing the communalities values, we will discuss what is the communality in later slides. So yeah, see. So there are different categories based on the different criteria based on the communalities. Based on this, we can choose different kinds of samples. And also we can say that whether the particular sample set can be used for the factor analysis. Okay. So are the observation independent? Observation means that independent means that each observation should be not related. Okay, so like correlation, the serial correlation, I think economic students might know that autocorrelation or serial correlation kind of things. So this kind of correlation should not exist for the factor analysis. Okay, so are the variables are sufficiently correlated? So since as I told earlier that the variables are the factor analysis and principal component analysis are highly based on the covariance and correlation, variance and covariance and correlation of the different variables we are using in the analysis, so that all variables should be correlated. So whether these are correlated or not as a whole, there are different kinds of tests are there. So yeah. So the first test is Kaiser-Meyer-Ogling test statistics, which gives some set of values. Okay, if this value is below 0.5, then the whole data set is not acceptable for the factor analysis. If it is more than 0.7, then we can consider for the analysis. And even if it is more than 0.9, so it is the data set is highly acceptable for the factor analysis. Okay, it's shortly called as a KMO test. So how to extract the factor? So there is a difference in the procedure in extracting the factors. There is a difference in the between the PCA and FEA. FEA separates each variable's variance into common, specific, and error variance, and use the common variance only for the for identifying the factors. Whereas PCA assumes all variants are common. It will not separate any kind of unique variance and error variance. It will take all variables as a common total variance. Okay, so let me explain this by this diagrams. See, if this fully for the principal common analysis, it considers the all variances are obtained from the different variables are common. Okay, it will not consider any kind of separation for the variance only associated with the variables. Okay, not a common variance or error variance. It will not consider any kind. Okay, see, but the factor analysis, it consider common variance. It decompose the variance into common and unique or error variance. And once it is decomposed, then for the analysis, the factor analysis will take only the common variance. It just leave the unique variance. It will not consider the consider it for the analysis. So let me explain this. What are the two these common variance and unique variance? Common variance refers to the portion of the variance in which variance in a variable that can be explained by the factors. That's all the factors. But unique variance is the portion of the variance that is unique to the variables, such as measurement error, other individual influences not shared with the other variables. That is not shared with these common variables. Okay. So that PCA seeks to summarize variables under broader components, while factor analysis identifies the underlying reason for correlations. These differences leads to the distinct interpretation and applications, and also these are all the softwares analyzing the factor and factor analysis and the PCA will have a separate packages for each analysis. Okay. So that how does the factor extraction work? Let's see. See, these usually this factor extraction will be done by the PCA. Its objective is to reproduce the data structures with only few factors. Okay, PCA does this generating new set of factors as linear composite of original variable. Linear composite of original variable. Let me explain this, which produces the original variables variance as best as possible. For examples, if it is our desired factor, this factor is generated. The value for this factor is generated by just adding the sum of weighted variable values. Okay, so this weight may be this is a linear composite. This weight may be the what just the correlation between this factor and this just factor loading. Okay, just this is called factor loading. So if this factor loading is 1, this factor loading, the value of the factor loading may be vary, maybe from 0 to 1, whatever. So it will give as the sum of all these the sum of product will give the score for the factors. Okay. So this here this weight is called the factor loading. So like that, based on the weight, we can extract the variance from the all the variables and generate as much as possible, and that is maximizing the total variance as much as possible and generated as a factor 1. Okay, then so then the factor 2 can be generated. What the left out variance after generating the factor 1. Okay, So these are called as the all these factors are called as a principal component or a factor. Like okay, that more precisely, this PCA computes the eigenvectors or factor loading. This actually the role of the PCA is just estimating this loading, then multiplying the respective values of the respective variable and computing the factor. Okay, so these weights, these are called eigenvectors or factor weight, extract the maximum possible variance of all the variables with a successive factor continuing until a significant share of the variance is explained. So actually this how it is operates, the generating the factor. The first factor is extracted in such a way that it maximizes as the variance accounted for in the variables. So for example, if in our vector space we have different factors and different variables. So as I said, so what all the variables are very close to this, that is the degree less than 90-degree angle, will give more variance to the respective factors. So if the variables are located 90-degree angle, then that means that there is no relationship between the factor and the variables. So like this, the variance of all the variables are just maximized and generated the score. Okay. So like this, after extracting first factor, the second factor is extracted, which maximizes the remaining variance accounted for. That is that. After extracting the factor, that captures the some amount of the variance and left out some amount of variance. So this left out variance captured can be again maximized and accounted by the second factor. And the third factor will also extracted based on the maximizing the variance left out by the factor 1 and factor 2 again. So like that, the subsequent factors are generated just by taking the variance, maximizing the variance left out by the previous factors. Okay. So what are eigenvalues? Here, the eigenvalues represents the amount of variance or information captured by a factor. Okay, from the total sum of variance by all the variables. It tells us how much of the original data's variability is explained by the factors. Let me explain this by these diagrams. See, look at this. This is just a sum of the variance of all the variables. For example, it is if standardize the variance of all the variables, that is variance of one variable is equal to 1, then sum of 5 variables will be will become the variance of the five variables. That 5 is a sum of the variance of all the 5 variables, because that the variance of each variable is just standardized to 1. Okay. So now, if a first factor captures a 2.1 variance of the total this 5 variants, and the second factors will maximize the variance 1.3 variance, and so on like this. For how many variables are we using? The generator variable factor will also be equal to the how many variables are we using. Here we are using the 5 variables. Then here 5 factors are generated with different maximizing the different amount of variance. Okay. So here, so if we divide this by the total variance, we will get the percentage of the variance explained by the particular factor. Okay, here, see, if we divide 2.1 by the 5, then we will get some 40 8 or something. I don't know exactly here that. So the second factor captures this. So combinedly, these two factors expresses the 68% of the total variance of the all the variables expressed. Okay. So like that, these are all the the eigenvalues are the just the amount of variance or information captured by the factors. Okay. So what are all the communality and uniqueness? So communality is just how much variance of each variables share to the extracted factors. Generally, these extracted factors should be account for at least 0.5. That is a 50% of a variables variance. Okay, it's just a communality is just a variance of each variable shared to the extracted factors. Okay, it should be above 0.5. Okay, that is a 50%. So uniqueness is just opposite to the communality. This represents the proportion of variables variance that is not explained by the common variance. The proportion of variables variance that is not explained by the common factors. Okay, but this value should be less than 0.5. So that so communality, either communality value should be more than 0.5 or uniqueness value should be less than 0.5. So that for that variables we can select those variables for the analysis. If it is not like that, we can reject those variables or remove those variables from the analysis data set. Okay. So communality value will be like this. So here see. So all the values are more than 0.5. So we can consider all these variables from S1 to S are fit for the analysis. So now we have to fix the number of factors. So in order to fix, so what how many variables we use, we'll get the those number of factors. The number of factors should be equal to the number of variables we are using for the analysis. So, but we cannot take into consider for all the factors for the further process of the analysis. We have to pick only the desired factors. So, in order to pick desired factors, we have some criterions. So, one is a Kaiser criterions. So, that is the previously we have seen that eigenvalue. That eigenvalue, the factor which have the more than one eigenvalues, that factors will be treated for the further process of analysis. Okay, so the reason behind for this, the each factors with eigenvalues greater than 1 accounts for more variance than the single variables. As the objectives of the PC and FA is to reduce the overall number of variables, each factor should account for more variance than the single variable it can. Okay, if this is occurs, then this factor is useful for reducing the set of variables. So these Kaiser criterions or latent root criterions can be used, commonly used criteria for determining the number of factors. Okay, so this is the result of the factor analysis. So here we can get the this eigenvalues here. So if wherever the eigenvalue is more than once, we can select these are the factors. Here we have used 5 variables and we got the 5 factors. So among these 5 factors, which factors have the values, the eigenvalues more than 1 can be selected for the further analysis. Okay, so which captures, see, look at the cumulative percentage share of this. It's 82%. So that means that the 82% of the variations explained in the variables are expressed by this 2 factor itself. Okay. So the another one criteria is a scree plot. See, this is a scree plot. It's just the plot representing the eigenvalue against the component number. So where this elbow shape is end. So before that, how many points are there can be counted as the number of factors should be selected. So here it ends here, only 2 factors. So then we can select the 2 factors here. It's called the scree plot. then determine the number of factors based on the expectations. We can also apart from these criteria, we can also determine the number of factors based on the our theory requires. Okay. And by subjectively we can give the select the number of factors we need. Then how to interpret the factor once we generate factors, how to interpret the factors. So we have for this we have to determine which variables relate to each of the factors extracted. So the for extracted if we for example, if you choose two factors, factor 1 and factor 2 by using the eigenvalue criterion, then how each variable are expressing the how much variance each variable express on the two factors. Based on this, we can interpret the factors. So actually, it is based on the factor. The factor loading is just nothing but the correlations between the factor and the variables, which ranges from -1 to +1. A high absolute factor loading indicates that a certain factor represents a variable well. Using the highest factor loading, we assign each variable to a certain factor, and then produce a label for each factor that best characterizes the joint meaning of all the variables associated with it. Yeah. So, but we have some problem in interpreting the solutions. So let's see here. So suppose we have two factors here, and these are all the variables. These are all the values of the factor loading. So here see the factor variable 2 expressing more factor loading for both 1 and 2. Okay, like that. If variable 4 is also like that. So in such a cases, we cannot select the variable. We cannot decide. We cannot take decision whether the variable 2 should be considered under the factor 1 or factor 2, like this for factor variable 4. So here we have some confusing situations when compared to the other variables. So we have to avoid such situations. So in order to avoid such situations, we have some procedures, that is factor rotations. Okay. Here just we rotate the only factor at by maintaining the same degree, that 90 degree of factor 1. So see here 90 degree of factor 1 and factor 2, just to rotate this factor 1 and factor 2. And now we have the look at the x1 and x2. X3 represents the factor 1, and x4 x5 represents the factor 2. Just changing the angle of the two factors, we can easily group the respective variables under different factors. So this is called factor rotation. So based on the changing the angle, if it is a constant angle 90 degree, and if we allow for the changes in the degree that less than 90 kind, we have the different kinds of rotations, that is orthogonal and oblique rotations. Orthogonal maintains the 90 degree angle as it is. Oblique rotations allows for the changes in the angle between the two factors. Mostly orthogonal rotations, there are different kinds of estimate methods is there. Varimax, Quantimax, and Equimax. Varimax is the by default in all the softwares, Varimax will be used. And but in SPSS we can choose even Stata and kind of things. We can also choose whatever the methods we can prefer. We prefer. Okay, like the for oblique rotations, the Promax is usually will be used for the rotation. Okay, by using these Varimax and Promax, we can rotate the factors and group the variables under different factors. So these are all the look at this. These are the before rotating the the loadings between the factors and variables before rotating the factors. It's after rotating the factors. Here, see, we cannot conclude here that here, for example, here we have a so variable s1 so variable s2 have a higher higher representing the higher variance both factor 1 and factor 2, like this. More or less there is a confusing things in terms of absolutes. But after rotating this, see here, see these are this have the low loadings, low factor loadings, and this have the low factor loadings. So after rotating, we can easily group this all from variable s1 to s4 under factor 1, and variable s5 to s6 under factor 1. Okay, so we can group these variables are representing by the factor 1, these variables are representing by the factor 2, like. Okay, so this is just a visualization of how this after rotation, how variables are grouped into two different factors. Okay, so then for allocating the this variables, we have some steps. Variables into different categories, different factors, we have some steps. First we have to examine the factor loading, then we should focus on the absolute values of the loading, both positive or negative values, just and assign variables highest values for the respective factors. If it's something or similar to 3 factors have equal values, like just more or less similar, then in such a case we have to give some based on the theoretical expectations we can assign. Okay, so like this, see, for example, here variable a, b, c. So factor loading for here factor 1 is 60 and 0.6 here too. Then automatically we can assign this variable to the factor 1. So here more or less similar. So based on the theoretical expectation, we can assign the variables to the respective factors. So here so these factor loadings are just below the our threshold levels. So then we can reject this variable from the groups. Okay. So finally we can group these variables under factor 1, these variables under factor 2. Okay. Then the final step is to that whether these the factors are fitting goodness of fit. Okay, so in order to that we have two different methods. The first we have to congruence of the initial and reproduced correlations. First we have the before the analysis we have a correlation between the among the different all the variables, and after the rotation we have a different kinds of correlations. See, look at this here. So this is after estimating the correlation after finishing our factor analysis. So this correlation should be compared with the correlation before we started the analysis, and we can also take a difference. If that difference is more than 0.05, those factors can be those variables can be treated as unfit, that there is no goodness of fit for that. So we can remove if such a case is more than 50%. So here see 0.056, 0.06, 0.09 all are more than 0.05. So these correlation are treated as unfit for the analysis, but the number of this unfit should be less than 50%. Here it is only 28%. So all the variables are fit for the analysis. in such a way we can say that there is a goodness of fit existing. Okay. So like that, we can also, for looking at the communalities, what we have seen in the previous, then we can say the goodness of it. If the communality for the respective variable is less than 0.5, so we can reject that variable. Okay. So finally, we can predict the factor score, and yeah, we can use for this factor source for further analysis. So this is the step for doing the factor analysis. So first, formulate the problem, construct the correlation matrix, determine the method of factor analysis, and determine the number of factors, and rotate the factors. Then interpret the factors. Then select the respective variables under different factors. And then you can use for the further analysis. So we have finished that. So what are all the procedures existing in the factor analysis and the principles component analysis? Let's go for some practical hands-on exercise. Okay. Yeah. Any question? So that is a factor. Yeah. So factor loading is determined by some just maximizing the variance of all the variables. It's just a mathematical. So there is a mathematical procedures behind that. Here we cannot explaining those things is just beyond the scope of these presentations. Okay, if you are interested, you can look at the further readings. Okay, it's just it's not clear. It's a just a mathematical expression, so that just maximizing. It's not clear. Okay, let's move on to the practical session. Okay. So I think I have shared the data set for you. In Excel sheet, it's there in Excel sheet. Here, see this S1 to S2 FA. It's a data set for this hands-on session. Okay. So here we have a number of so many variables, and we are going to take only the S1, S2, S3, S4, S5 up to X6. Okay, here see S1, S2, S3, S4. These variables we are going to take for the analysis. See, so by doing for doing the factor analysis, just to go to the analysis and dimension reduction analysis. Under the analysis menu, dimension reduction options, and choose the factor. So you can get the one dialog box like this. Then you have to select the variables you are interested in doing the factor analysis. So here our interest is all S1 up to S8 variables, S2, S3, S4, S5, S6. Okay. So now we have here different options. Okay, just click the descriptive statistics. Here we have different options. Here we have to choose KMO, that whether the particular all the variables are correlated or not, highly correlated or not, to check in order. Hi.
Sir, we don't have the data set, sir.
So I have a data set இல்லைன்றாங்க mail. Yeah. So I think it's already said. You just check the mail, your mail. So no,
Sir, we
okay,
can
that you can get your data even after finishing this. Just listen to the session.
What is the file
Okay.
name? What is the file name, please?
S1 dash S8 underscored factor analysis FA. See here, see where is it? Yeah. So this is a file name. Can you see?
Yes, thank you.
Yeah, thank you. So that first that our the initial step is whether we have to check all the variables are correlated or not. So in order to that, there is a we have seen that KMO test. So we have to check that. Then click continue. Then click extraction here. So principal component will be used as a extraction method of the extraction of the factors method, and the criteria for selecting the factors is eigenvalue should be more than one. So if you don't want use this criteria, then you can fix manually whatever, one or two or whatever. But as a default, by default, it will be the eigenvalue should be greater than the one. Okay, then if you want to check the number of, here also we can select the scree plot. Then if you want check the correlation matrix, so you can click the correlation. Then click continue. Then rotations, we need the rotations that we can choose any kind of rotations that here we can choose the varimax, and click the loading plots and rotated solutions. Then continue. Then now click the scores. If you want to save the estimated factor scores, then you can in the data file, then you can click and save any kind of this. Okay, for the regressions, for the further analysis of regressions, you can choose like display factor scores, coefficient matrix. That we don't need, I think. Then options. Suppress small coefficients, like you can choose. Okay, now just give. Okay, we can get results. So this first table shows the KMO and Bartlett test. Here see, by looking at this value, this 0.9. So we have seen that if this value is more than 7, it will be all the variables are appropriate for the analysis. Here we are getting 0.9. So this is so that means that all the variables in the model are good for the factor analysis. And also we can check this Bartlett test if it is a significant. So here null hypothesis, all the variables are not fit for the analysis, is a null hypothesis. We have to reject this null hypothesis. So here we have the significance 0, committing type 1 error 0.00. Even if you at 1% level, it shows the significant. So we can reject the null hypothesis of not all variables are correlated. That means that all variables are correlated. That's the hypothesis testing. Then by looking at the communality values, here we have seen that if the communality value is 0.5, then for those variables we can select for the analysis. Here all variables is also more than 0.5, then all factors are perfectly fit for the analysis. Okay, so this is a table, the agent tables, what I shown in the slides. So this shows the agent values. So if this agent value is more than 1, we can these are all the factors, the number of factors which are equal to the number of variables. So these first two factors can be selected as our new variables or latent variables or principal components, like whatever we can say this. because these agent values are more than 1. This is our criteria. Okay, it represents see, look at the cumulative 82% of the total variance. Okay, expressed by these factors. Okay, so by looking at the scree plot, we can say this two factors can be selected for the analysis. So this component matrix gives the factor loading, that the correlation between the factors and the variables. These are all our two selected factors. These are all the variables. So how these are correlated? Okay. So by looking at, see here, we have a confusing correlations because both factors are represented highly represented by the some of the factors. So we have to rotate the analysis as a angle of the factors, and again we have to look at the component matrix, that factor loading after rotations. So now we can find that 5 S5 to S8 have a high correlations with factor 1, and S1 to S4 have a high correlations with factor 2. Okay, then we can that means that these variables are coming under the latent variable 2, that is a factor 2. Thus these variables are coming under the latent variable 1. Yeah. So these are all the how the variables are grouped under different factors. Okay. So we can get there's a goodness of it. Correlation coefficients. So just reproduced correlation. Yeah. So now we can check the goodness of it of the factors like this. These are all the reproduced correlation matrix. This represents the difference between the reproduced correlation matrix and before the reproduced correlation. Okay, that is I think initially we will get. So the difference between these correlation matrix should be less than 0.05. Here, as we seen in the previous, that we have 8 observations which are more than the 8 correlations, which are the difference between the two correlations of 8 is more than the 0.05. So that is account for 28% of the data. So that it is a less than 50%. So then we can say that the model is fit. Okay, like this. Then we can see the estimated factors here. So in the data sets, okay, see factor 1, factor 2. These are all the estimated factor scores. Okay, this can be used as for further analysis in regression, either in dependent or independent variables, as we decide. Okay. So okay, this session is I'm finishing this session at this time. So what are the doubt you have? Just leave message to the organizers. Then as I said, that effective, efficient questions will be taken and will be answered. Thank you. So I would like to thank the organizations for giving me this opportunity. I encourage them to conduct such kind of programs in future also. It will help the many scholars at some minimum cost. Thank you so much for your